Okay, hello and welcome. I am the disembodied voice in the ether, and yeah, today we are going through an AS physics paper. This is the first one for the week, and this one is multiple choice. There are 40 questions on the paper, and a lot of them, like the two that you can see in front of me here, are quite simplistic. A lot of the multiple choice papers are essentially all about knowledge. They're just things that you need to know. Because there are so many questions, because the paper is actually quite long, despite being multiple choice, I'm going to be essentially just skipping over those almost completely. That's about it, really. So this first question, this is just requiring you to know what units are SI units and what aren't. The second one is just about your prefixes. I need a pencil. There we go. Right. So, question 3. So this one is dimensional analysis, essentially. So pressure is newtons per square meter, and density is kilograms per meter cubed, and then you end up needing to put it to the power of a half to make it into a velocity. Not a great deal to say here. I will just once again make the point that I frequently make with these, which is I think for complex units like pressure, for instance, and indeed that from force, it's often easier to try and work out the units from equations. So force equals mass times acceleration, and then pressure equals force over area. And that will allow you to develop the units from the SI units without having to remember one giant long unit in one go. Alright, so we have an experiment, and this one is about errors. So current and potential difference, and we are calculating the resistance. So alright, so this is one that is about percentage errors, in fact. Okay? So, yeah, it's important to note that we're being given plus or minus errors. We're not being given fractional errors. But because we have V equals I over R, it means that our resistance, I over V, is multiplicative. So we're dividing, in fact, but it's multiplicative in terms of how we are adding our errors. Therefore, it's the fractional errors that we need to add. So you would need to work out what fraction these two errors were, and then do that fraction of the overall 8. All right, let's move on. So, Young's modulus. Which measurement has the larger... Okay, so more uncertainties, and here we are dealing with this equation. It's all multiplicative, the d is squared. So what we are looking for here, ultimately, is once again fractional errors. That's what's important here. So you're looking for the largest fractional error, and you are noting that for d, because it's squared, you're doubling that fractional error when you compare it with the others. Okay. A tennis ball thrown horizontally. So if the effective air resistance is not negligible, so this is the unusual, what happens to the horizontal and vertical components? So okay, so they're kind of assuming that it's falling an incredibly long way here. So essentially, they are looking for what is happening after a really long time here. Because the horizontal component will decrease to 0 eventually under air resistance, because it has air resistance. But it would have to travel for a really long time for that to happen. So debatable, but yeah, the answer is D, because essentially the point is that your air resistance eventually means that it's no longer accelerating, and indeed that it decelerates to 0 in the horizontal direction. Okay, object thrown, and we have an acceleration on the moon, so a very small acceleration. What is the time taken? So this one is a SUVAT question. It's fairly simple, really. You're looking for the time for its velocity to reach 0, and then you double that time because it's going to return in the exact same time that it went up. So you're looking for, in SUVAT, you're looking for v, the final velocity, equals 0. Okay, we have the acceleration of an object moving in a straight line. Which graph shows the variation with time of the velocity of the object over the same time interval? Okay, so they've written the same thing on 2 pages. That's slightly confusing, but there we go. So, acceleration, low here, high in the middle, low at the end. So we are looking for a velocity that is increasing slowly at the start, quickly in the middle, and then slowly at the end. Okay? Because all of this acceleration, remember, is increasing the velocity. It's all positive acceleration. That's the key point here. So your velocity is always going up. It's just a matter of how fast is it going up. Going up slowly, going up fast, going up slowly. Whereas in these two, both, in B and C, the velocity has gone down at some point, and in this one, the velocity is always getting faster and faster. Okay. An object of mass 4 kilograms moving with speed 3 meters per second strikes a stationary object in an inelastic collision. So we have total kinetic energy of a half mv squared, which is a half times 4 times 9, which is 18. It's inelastic, so we are losing energy. Therefore, our total kinetic energy is less than 18 joules. These two about before are just rubbish. And this one would be so this one, B, is the elastic collision, is the inelastic collision as they've asked for. Sorry, my apologies. A would be the case if it was inelastic. If it was elastic. Oh my word, I'm sorry. Right. Yes, A would be the case if it was elastic. B is the case because it is inelastic. C and D are just wrong. Okay. Right. Momentum changing with time. So, resultant force. Force is the rate of change of momentum. We have changed 500 kilogram meters per second over 10 seconds, so we have a resultant force of 50 newtons. There we go. That was nice. I've always found it slightly unfair that, in a multiple choice paper, the easy questions are rated just as highly as the hard questions, but there we go. So we have some force diagrams. A string is attached to the same point on the picture. We have shorter string in diagram 1. What can we say about the magnitude of the forces? So, we know for a start we can eliminate C and D. R1 equals R2, because ultimately we are holding up the same picture. Okay? The second point. So, this is about sine graphs. So, a smaller proportion of the T1 is going to go into a smaller proportion of T1 is going to go into holding up the picture in the vertical direction than of T2. And so T1 is going to need to be larger in order to hold up the picture, because most of T1 is actually just pulling horizontally, because it's at a shorter angle. And therefore the answer is going to be B. A man is holding a 100 Newton load stationary in his hand. That's 10 kilos. That's a That's a solid bicep he's got there, but fair play, you know. Strong man. The combined weight of the forearm and the hand is 20 newtons. Sounds like quite a heavy forearm as well, but there we go. No, that's a very light forearm. That's a 2 kilo forearm. That's a very light forearm. Okay, interesting numbers here, but we'll go with it. So we have a nice horizontal, we're a right angle triangle, essentially. What is the vertical force F needed in the biceps? So this is just, I don't know what you call it, but our moment M is equal to force times the perpendicular distance. In this case, everything is perpendicular, and so our bicep is pulling up by here with a certain separation here, and that is going to need to balance the other two. So we have anti-clockwise moment from the bicep needing to balance our 2 clockwise moments from the arm itself and the weight. So essentially what you are looking for is find the moment from the weights total and then divide it by 4 centimeters. There we go. Okay, we have a spindle. Hopefully not poisoning anyone. We have a spindle. We are attaching. Okay, so this is an interesting and overcomplicated diagram. We have a lever of length 1.2 meters. At its other end, the center of the disc of radius 0.2 meters. Passes pulley attached to 900 Newton weight. Minimum force F applied to each end of the lever that could lift the weight. So, spindle transfers moment. That's the important point. Okay? So, the total moment applied by our force F is going to be F times half the distance, the perpendicular distance, which is 0.6 meters. That is going to be transferred down to the disc, but because the distance is now shorter, we're going to get a considerably larger force coming out of the disc. This is just a right angle pulley, so our right angle pulley doesn't change the force in any way, and therefore that force coming out of the disc is going to need to be 900 newtons, and therefore you can go backwards to work out our force here. Very complicated diagram. It's all still about moments. It is essentially saying that you need a 900 Newton force here, and we're matching moments. That's all we're doing. Alright, so average power output of a laser, 0.2 joules of energy in 10 nanoseconds. Power is energy per second. 10 nanoseconds just converted into seconds, that's 10 times 10 to the minus 9. 0.2 divided by that, put it into your calculator, and you will get your answer. 0.02, 10 to the 9, it's 20 megawatts. Cool. Okay, a weight, W, hangs from a trolley that runs along a rail. The trolley moves horizontally through distance P and simultaneously raises the weight through a height Q. Interesting. Okay, that's a oddly contrived question, but there we go. So, the weight moves through the distance r from x to y. It starts and finishes at rest. How much work is done on the weight during this process? So, this is an interesting question. The actual answer that they are looking for is, or should be, WQ. Yes. So, the important point and what they want you to realize here is that work, and this is one of the more interesting questions on the paper in conceptual terms, work is the distance done by a force in the same direction as the force. So if we have a force F in this direction, any distance that we are moving has to be in this direction for it to do work. Okay? So our weight W, which is the force that we are in fact acting against, our reaction force working against that is what's doing work. So we have a tension W that's pulling our weight up. That's doing work. And so it's only the Q direction where we actually do work. Horizontally, there is, in theory, no force, in sort of inverted commas, acting. It's worth making the point that there does actually have to be a force, otherwise it would never move, but we're neglecting it in this case because it would actually be sort of work done against air resistance or something slightly odd like that. So we're going to ignore it. The important point is, work done is the force times the distance moved in the direction of the force. That's what this question is really all about. Okay, I'm slightly surprised that they didn't have a W. Oh yeah, yes they did. They have a W. Okay, cool. That's the one that they're expecting people to kind of trip up on, because that's the actual distance they've moved. But the work is only acting in the vertical direction. Okay. The engine of a car exerts a force of 600 newtons in moving the car 1 kilometer in 150 seconds. What is the average power output of the engine? So, power is energy per second. It's energy divided by time. We can get our energy by doing our work done is force times distance. So, we have in fact done 600,000 joules of work. Divide that by 150 seconds, and you will get your answer. That should be 4 kilowatts. 17. Which statement about boiling and evaporation is correct? So this is just a learn it one. Yeah. I think they're looking for C there. No, they're not. They're looking for D. Okay. That depends almost entirely on your definition of evaporation. But yeah, so they were looking for D. That's just a learn it type question. I would be tempted to argue with that, but I'll be quiet. I will be a good child and not argue with the examiners. That never ends well. Trust me. Even if you're right, don't argue with the examiners. Exam technique 101. Right. Okay, so one temperature at which water, water vapor, and ice can coexist, the triple point. Which statement? So this is just another learn it one. I'm going to skip over these because I want to get through the paper. These are just things that you need to learn. No, okay. Let's just continue on. Okay, crystalline solid is heated at a constant rate, and the change of temperature with time is shown on the graph below. So, here is our phase transition. If we are heating and our temperature is not going up, that means we have latent heat and we're going through a phase transition. They're making a statement. Okay, so they're looking for B. They're assuming it's melting. So they're assuming that you're melting here and therefore you're going from solid to liquid. Fair enough. Okay. Stress-strain graphs for 3 different materials are shown, not drawn to the same scales. Fair enough. Our 3 materials are copper, rubber, and glass. Okay, so which materials are represented by the graphs? First of all, glass, straight away. It's breaking. Breaking means it's glass, probably. We would hope. So, yeah. We're looking at, this should be copper, rubber, glass, I should think. What are we on? We're on 20, aren't we? Yeah. Copper, rubber, glass. Yeah. So, glass, it's breaking up here. That's a thing that glass does, not so much the metal and the rubber. Metal is elastic for a bit and also has a very sharp, like highly angled stress-strain graph because it's hard to bend. And then after a while it becomes malleable if you apply enough stress. Rubber is rubbery. It's stretchy. It's elastic at low stresses, and more to the point, you can stretch it quite easily. Okay, let's move on. We have load extension is just stress strain, but with units. That is exactly the same thing, right? Load in kilograms is actually just force if you convert that to newtons using gravity, and extension is, so strain would be extension divided by the total length, or as a percentage of the total length. But it's the same idea, right? It's the exact same thing. So we are elastic because we have a straight line. How much work is done on the wire to increase the extension from 10 millimeters to 20 millimeters? So, we are looking for area under the graph, essentially, and then converting these into converting this one into force. Turn this into force by timesing by G, 9.81, and then area under the graph using the force rather than that. Or alternatively, area under the graph and then multiply by G. But that method, while simpler, below is a little less understanding. Anyhow, let's move on. Longitudinal waves, so this is just a learn it question. D is the answer. All of the rest of them are only true of transverse waves. Not much to say there. Order of magnitude of the frequency of the longest wavelength ultraviolet lights can be expressed as 10 to the x hertz. So this is just a learn it question. I have no idea off the top of my head, I have to admit. That's just one that you need to learn. It's not very interesting. I guess it's a pub quiz fact, if nothing else. But there we go. Okay, the speed v of waves in deep water is given by the equation blah. So we are looking at essentially, so actually this is an experimental question more than anything. You will come across this more in your experimental paper. Essentially, in an experiment, you always try and plot a straight line graph. Lambda is the wavelength of the waves, g is the acceleration of freefall, blah, blah, blah. What graph will give a straight line through the origin? So, okay, so that's slightly curious. So, what they're asking you to do here is to substitute in. So, they're looking for v equals f times lambda for any wave. That is always true. That is essentially the definition of f and lambda more than anything else. So you substitute these in here and you will end up with f squared equals g over 2 pi lambda. And therefore you can plot f squared against 1 over lambda to get a straight line graph, because that links with y equals mx, where your gradient m is your g over 2 pi, and your 1 over lambda is x, and your f squared is y. That is actually a very important one to pay attention to, because that is this sort of idea of turning something into a y equals mx, usually mx plus c, but in this case there is no plus c, is very important for for all sort of experimental ideas later on. Okay, we have a stationary wave on a stretched string. It's got 3 loops going on, so it's 1.5 wavelengths. So Q and S vibrate in phase because they're the same point essentially. P and T is 3 half wavelengths, so that's wrong, but that's the other one that they're trying to get people to miss out on. So this is the trick, if you like. This is your kind of trick part. It looks, there's obviously 3 gaps. That's the bit they're trying to catch you out on, right? R is obviously the opposite of the truth. D is just not, it's wrong, but it's not anything particularly interesting. C is the catch you out one. B is the truth, the ultimate truth. 42 and all that. Continuing on. A parallel beam of white light passes through a diffraction grating. Orange light of wavelength 600 nanometers in the 4th order diffraction maximum coincides with blue light in the 5th order diffraction maximum. What is the wavelength of the blue light? So, the whole question is apparently utterly irrelevant, as far as I can tell. Yeah, you're told nothing about this diffraction grating. So, essentially, this is annoying, right? Because realistically, are they not just literally asking purely this bit? I don't know. Maybe I'm missing something here, but they are just asking you for the wavelength of blue light. And that's it. Or are they? No, okay. Perhaps. No, okay, they're not. Okay, this is, so n lambda equals d sine theta. Okay, this is actually the equation for double slits rather than diffraction grating, but the point remains the same. We are looking for n lambda. And so ultimately what we are looking for here is that 4 times 600 equals 5 times our, what should we call it, our blue light. That's a 5, not an S, by the way, but you get the idea. Equals 5 times our blue light wavelength. So 2400 divided by 5, 480 nanometers. Yeah, these are all fairly bluey. That's getting in towards green. That's definitely red. So these two, you know that they're wrong off the start because that's red and that's pretty green. That's like turquoisey. These two are pretty blue. So that's fair enough. Okay. So yes. All right. Note production in a horn is to set up a stationary wave in an air column. This is actually true of basically all instruments, pretty much. Almost all instruments set up stationary waves in some form to produce music. Most of them in air, apart from string instruments, where it's unsurprisingly on a string. For any note produced by the horn, a node is formed at the mouthpiece and an antinode is formed at the bell. The frequency of the lowest note is 75 Hz. What are the frequencies of the next 2 higher notes for this air column? Interesting. So this is essentially requiring you to consider what this has to look like. Okay? So node at the mouthpiece and an antinode at the bell. So I'm guessing will they allow you to have just this where a genuine like quarter wavelength goes to here? I'm assuming they would. That would make the answer B. Is the answer B? No, the answer is D. Yeah. Okay, cool. So, this is the first one. It is then worth noting that the second thing which will do this same thing, the second thing that will do the same thing, that's very eloquent. The second wave that will also give you an antinode here and a node here is then going to have to do this. And so what you're actually looking at is essentially anything that's forming a proper stationary wave over double the length. Okay? So your first wavelength has a whole wavelength across one double the length, the second one 3, the third one 5, and so on. And so you're going to go 1, 3, 5, 7, 9, etc., etc. And so this is 3 times 75, and this is 5 times 75. Yeah, okay, that'll do. Moving on. We have a beam of electrons. We are going to... Okay, so this is just nice and simple electrical force. So we have an electric field, which is a potential difference divided by the distance. So 8 of 2 should be 4, and then you're looking for your electron charge multiplied by that. So yeah, in this case, electric field is potential difference divided by separation. Potential difference total is 8 divided by separation is, which is 2, gives you a 4 newtons. And then it's 2 centimeters actually, but the point stands. And then you're just multiplying that by the charge of 1 electron to get your force. Yeah, okay, that one's not too bad. Right, moving on. Okay, we're 3/4 of the way through. We're not doing too bad. The diagram shows 2 points, P and Q, which lie 90 degrees apart on a circle of radius r. A positive point charge at the center of the circle creates an electric field of magnitude E at both P and Q. Yep, we have a circle. Cool. Which expression gives the work done in moving a unit point positive charge from P to Q? So, this is a slightly fun one. The answer is A, 0. The reason for this, you can look at this in 2 separate ways. Okay? One of them is to say our force is always going off in the radial direction. And so if we were to take a point charge and move it along the circumference of our circle from P to Q, we would never be moving in the direction of the force. We would always be moving at a right angle to the force. And if you do that, you're not doing any work, like we saw in an earlier question. Therefore, total, you do no work. The other point to make is that given that they're the same distance from the charge, they are actually at the same electric potential. And so if your potential energy hasn't changed at all, then you haven't done any work, you haven't changed anything, because it's a conservative force. So you can look at that in either way. They're both fairly interesting. Okay, so 2 electrically conducting cylinders X and Y are made from the same material. Their dimensions are as shown. So this is looking for our resistivity equation. So this is R equals rho L over A. Resistance is proportional to length, inversely proportional to area, and proportional to resistivity. Resistivity is a property of the material. These are the same material, so that's actually irrelevant. Okay? Note I was halfway through saying A and area. Area is proportional to d squared. Therefore, we're going to have 2 to 1 y over x, which is 1 over 2 x over y, or it should be. Oh, other way around. Sorry, my bad. A is on the bottom. I'm being foolish. I apologize. But yes. So, moving on. A battery with a constant internal resistance is connected to a resistor of resistance 250 ohms. The current in the resistor is 40 milliamps for a time of 60 seconds. 6 joules is lost in the internal resistance. energy supplied to the external resistor during the 60 seconds, and the EMF of the battery. Okay, so 6 joules, 40 milliamps, 60 seconds. So you can look at this in a variety of ways. The best way is to say 6 joules over 60 seconds. That can give me a power. 6 divided by 60 is 0.1 watts in our internal resistor over here. We have a current, we have a power, so we can get a voltage, which will give us our EMF. And once we have that, we can work out our energy going elsewhere. The other point is that our current is the same because they're in series. Therefore, from our current and our time and our resistance, we can work out the total energy dissipated. So those are essentially two separate calculations. Yeah. So not too bad. A little, how do we put it? Requires just a little bit of thinking your way around it. This is a question about taking stock of what you know. They've given you a whole variety of information, and it's okay, what can I do with it? If you are struggling with a question like this, what I would recommend is just writing down all of the relevant equations. So power equals, or time times power equals energy, and then power equals current squared times resistance, P equals IV, etc., etc., and anything else that you can come up with. Just write down any and all of the equations that are relevant, and then start trying to fit things into them once you can see it all in front of you. If you are struggling. If you aren't, then don't worry about doing that, obviously. But yeah, that can be helpful. In the same way that, if you don't already, probably should, if you're doing a SUVAT question, you write all of the SUVAT equations out. It's the same idea. Resistance changes with temperature, that's B, that's just to learn it. Voltmeter of resistance RV, and an ammeter of resistance RA. Okay, so we're dealing with imperfect voltmeters and ammeters. Which condition is necessary for an accurate value to be obtained for R? So the most important one is that R is much greater than RA. V is in parallel, so it doesn't... Wait. Yeah, V is in parallel, so it doesn't make that much of a difference, since it's only measuring the voltage, and the voltage in parallel is the same. A is in series, so... Wait, or does A ignore its own? Okay, this is slightly confusing. Hang on. What are they looking for? They're looking for 33A. They're looking for R is much smaller than RV. Okay, so they're assuming that A ignores its own resistance. That's fair enough. That's a good idea. So, actually, what we are looking for here is A is in series with the entire parallel system. Okay? V is only in parallel with R. And so V will be doing its job properly regardless of what A is doing. A is entirely irrelevant to our voltmeter. However, A is measuring, what A is actually measuring is the resistance of this whole block here. And for the voltmeter to be essentially irrelevant, it needs to have a very large resistance so that essentially none of the current is really going through our voltmeter. That's the idea. Yeah, okay. So that's what's going on there. So when we talk about voltmeters, usually we assume that there's no current going through them. And the reason that we assume that is voltmeters are designed to have a massively high resistance. The idea being that when they are put in parallel with something, all of the current flows down the easier path through R, because R is much smaller than RB. If that makes a little bit of sense. Okay, we have a circuit. We have identical resistors, and we now have negligible ammeter resistances. we have A1 0.6 amps. Our battery's in the middle down here. What are the readings on the other ammeters? So there we go. That's interesting. All right. So this is actually a slightly curious exercise. Ultimately, what we're looking for here is junctions. So we have a battery by here. So the idea is that it's going to have to come out of here, go one way and the other way, and then come back in down here. Conventional current flowing from plus to minus. Therefore, A2 is our total current. A1 has to be equal to A3 plus A4. And all of them have to add up to A2. So yes. And then the other thing is dealing with parallel currents. So the comparison between A3 and A4, A3 should be 3 to 1, essentially, which it actually is in all of these. So that's kind of irrelevant. So what you are looking for is these two need to add up to, they should be adding up to 0.6, shouldn't they? I'm convinced those should be adding up to 0.6. Why aren't they? Okay. Fair enough. All right. They're working off a slightly different principle. Okay, so we're looking at this. So A2 is our total current. A1, A3, and A4 have to add up to A2. A3 has to be 3 times A4, but that's actually irrelevant because that's true of all of these things. So that doesn't actually help us any. So yeah, slightly curious. So what you need is to look for one where these two plus 0.6 adds up to this one. That's what you're actually looking for here. Following on from that, you are also looking for a set of ratios. So this one should be double this one. So the idea is that if you have resistances, current tries to follow the path of least resistance in that ratio. So A3 has half the resistance, so the third root has half the resistance of the first root. So we should have twice as much current going through this one as this one. Similarly, this one has a third of the resistance of this root because this one's got 3 resistors. Therefore, we should have 3 times as much current going through here as going through here. And the way we can work this through, the simplest way actually, is to just say, okay, this one needs to be double this one. I already know that, so I know that that needs to be 1.2, and there's only one with 1.2. So that's actually the simplest way. So the key point for this one is the idea that, let's write this down, in parallel, double resistance goes to half the current. And the same principle for, a third or whatever it is, it's ratios. That's your key point here. I think that's a useful takeaway from this. Okay, right. let's try and get through the rest of this quickly, because this has dragged on a fair bit now. 40 questions is quite a lot. Potential difference, how many electrons? So this is just looking for potential difference is essentially that is energy per unit charge. So 4.8 joules divided by 2 volts tells you how many units of charge need to go through, and then divide that by the charge of 1 electron to figure out how many electrons. Resistance between P and Q in this network of resistors. So this is a whole set of parallel. So this is 3 things in parallel with one another. Add up the 2 side roots, and then 1 over RT is 1 over R1 plus 1 over R2 plus 1 over R3. This is radiation. This is what absorbs what kind of radiation. So alpha, sheet of card, beta, aluminium, gamma, lead, but beta has a negative charge, alpha is positive. So there we go, C. Yeah, that's just lots of information packed into one question, learning about the types of radiation. 2-proton radioactive decay of an isotope of iron was observed. What could be the resulting product? So when they say 2-proton radioactive decay, I think we are assuming that we are losing 2 protons, which would mean you get chromium. Yes, so we're just losing 2 atomic number, but they're decaying into neutrons, is the idea, I think. No? No, okay, so we're assuming that we're actually losing 2 whole protons just gone. So we're losing 2 of the actual proton number, but we're also losing 2 of our particle number in total, because the protons are gone. And so both of them are going to go around the line 2, and we're going to get this one. A double ionized uranium atom has a nucleon number of 235, proton number of 92. How many particles are in this ionized atom? So 235 nucleons, we would have 92 electrons to match the 92 protons, except we've doubly ionized it, so we have 2 less. So we're looking for 235 plus 90, which is 325. And then the last one, the grid shows a number of nuclides arranged according to the protons and neutrons. Decays by emitting a beta particle. What is the resulting nuclide? So lithium 38 emits a beta particle that turns a proton into a neutron. And so we are going to go up 1 neutron and down 1 proton. We are going to get D. No, we're not. Wait, emits a beta particle. Yes. What am I saying? Oh dear. I've been talking for far too long at this point. Beta particle turns a neutron into a proton. So we go up 1 proton, down 1 neutron, we get A. Okay, this has gone on a very, very long time. There we go. This is all you're getting on it though, so I suppose that's fair enough. This has been about 40 minutes on a multiple choice paper. I think in future it would probably be best to do multiple choice papers perhaps in person, so we can focus on just a few things. Going through the whole paper like this, I don't know how helpful it's been. Yeah, feedback would be appreciated on this. Definitely for the multiple choice format, this could use some improving, I feel. So, feedback from anyone who watches this would be much appreciated. Tell Tom, he can tell me, or tell me directly if you see me. And with that, I will leave you. I will disappear into ether once again. And yeah, see you again soon. Goodbye.